Hello dear learners, this is Dr. Sedhupathy, Assistant Professor, Department of Computer Science with Artificial Intelligence and Data Science, Dr. SNS Rajalakshmi College of Arts and Science, Coimbatore. Today we are going to discuss about computer system organization, which comes under basics of operating system or requirements before getting entered into what OS is actually. So today's agenda for the discussion will be like what computer system organization is actually and what is the difference between computer system organization as well computer system operations, what are the common function of interrupts and how interrupts can be handled and how interrupt timeline held inside operating system and input output structure, storage hierarchy, and what are storage device hierarchies, how it is actually differ from storage structure, and what is caching and what is direct memory access structure, and how a modern computer works. There is different type of hardware components of a computer. Those are all connected with a common bus. One or more central processing units controls all the hardware components which are connected together. Basically, the hardware components connected through bus, and those memories are stored in main memory. Concurrent execution of central processing units and devices competing for memory cycles. And there are a certain list of computer system operations basically happened inside operating system. Input output devices and the central processing unit can execute concurrently. Each device, it has its own controller, which is the charge of particular device type, which is the main authority of controlling each and every device type. Each device controller has a local buffer or local memory which holds the address in which that particular hardware components are connected through its memory. CPU moves data from and to main memory and to and from the local small buffers. Input output operations is from the device to local buffer of the controller. Device controller informs central processing unit it has finished its work by causing an interrupt signal. Once operating system receives any interrupt signal which can able to understand that any device has started its work or the device has ending its work. And common functions of interrupts. Interrupts actually transfer service routine control through interrupt vector. The functionality of interrupt vector is which actually transfer the service signal routinely to the main memory of all the service routines. Interrupt architecture must save the address of the interrupt instruction. And then a trap or an exception is a software generated interrupt caused either by an error or user requests. So actually an operating system is interrupt driven, which means all the operating systems are functioned by receiving and giving instructions by getting interrupt control or interrupt driven. How interrupts are actually handled? The operating system preserves the state of the central processing unit by storing registers and the program counter, which determines which type of interrupt has actually occurred, whether the interrupt signal is from the user or it may be from error happened during some task. So these are actually classified by means of pooling and vectored interrupt system. There are separate segments of code which determines which type of actions can be made for each interrupt received. There is a diagram to understand what are the interrupts and what are different types of timelines. When you receive an IO request, interrupt is changed from idle to transferring. And once the transfer done, the interrupt signal again goes back to idle state. So you can understand from the things like bottom line. And again, if you receive an input output request, the signal is transferred to transferring mode. Once it's done, it again moves to idle mode. As far as concerned with the central processing unit, user processes executing in the top line. Once IO interrupt process, the signal moves down. And here is the input output structure. After input output starts, the interrupt control returns its signal to the user program only upon IO completion. Until then, it waits in section, idle the CPU until the next interrupt occurs, waiting in the loop up to receives another signal. At most cases, one IO request is outstanding at a time. No simultaneous IO operations are actually processed. After IO starts, control returns to the user program without waiting for IO completion. So, which is the system call. So, what happens? The system call IO request happens. It actually requests the operating system to allow the user to wait for the IO operation completion, because already some signal interrupt is initiated, that particular IO is in execution process. So user is supposed to wait until the completion. And the next state is device status table, which actually contains entry for each IO device indicating its type, which means what type of IO device is in process, and the address of IO device stored in the main memory, and what is the actual state of that particular device. And operating system indicates into IO device table to determine device status and to modify table entry to include interrupt. If an IO device request is appeared or request is received from the user, the signal updated in that particular table. And here is the storage structure. Actually, inside operating system and inside the hardware components, there are different type of memories. There is a main memory. It is only large storage media that the central processing unit can access directly. Sometimes it may be classified as random access or typically volatile memory. And secondary storage, it actually extension of main memory that provides large non-volatile storage capacity. So what actually non-volatile is? It is actually a memory it can able to use during the system runs, power on, after the switch on. Once you switch off or shut down your computer, all the content stored in the volatile memory erases. But whereas in non-volatile, it stores, it has the content even you switch off. And coming to hard disks, it is a metal or glass plates covered with magnetic recording material. It stores all the contents. Disk surface is logically divided into tracks which are subdivided into sectors. The disk controller determines the logical interaction between device and the computer. And another one type of storage structure is solid state disks, which are actually very faster than the hard disks. Also, it is non-volatile. So nowadays there are a lot of technologies as comes and lot of technology innovations are introduced by means of storing content. It may be a glass material or it may be disk material, digital. The lot of digital formats are in popular. Coming to storage hierarchy, actually storage system organized by means of hierarchy, which is it may be belongs to speed or it may be of cost or it may be of volatility or volatile memory or non-volatile memory. And one more important content you supposed to keep in mind, that caching. Caching is nothing but copying information into faster storage system, which is main memory can be viewed as a cache for secondary storage, and the device driver for each device controller to manage input-output operations. It actually provides uniform interface. It acts as an interface between controllers and the kernel. What kernel actually is? Actually, we discussed what is the functionality of kernel in the previous video. And here is the diagrammatic representation of how storage device hierarchy. The topmost priority goes to registers, and then cache memory, main memory, solid state disk and hard disk, optical disks and magnetic tapes. So you can understand the hierarchy level from this diagram. And coming to caching, there is a most beautiful principle, for caching. It performed at many levels in computers, in hardware, operating system, software, and so on. So information in use copied from slower to faster storage temporarily is called caching. Faster storage initiated or defined first or accessed first to determine if information is available or not for further processing. If it is not, and then control moves to the secondary memory and fetches the required data from secondary memory to the cache memory. The information is used directly from the cache at the beginning. If there is no data, then it is actually copied from the secondary memory to the cache memory. Basically, cache memory is smaller than the storage being cached. Cache management is most important design problem nowadays. There are a lot of upgradations are happening for controlling cache memory. Cache size and replacement policies are basically routinely updated. So we discuss in the upcoming videos about cache memory. Now we just getting into operating system operations, and now into direct memory access, DMA. It actually high-speed I/O device which able to transmit information close to the memory speeds. Device controller transfers blocks of data from buffer storage directly to main memory without CPU intervention. So which is actually called direct memory access, without the interrupt of the CPU intervention. Only one interrupt is generated per block of data transfer rather than one interrupt per byte. So here is the modern computer, how a modern computer works. There is an instruction and data which stored in the memory, and there is a thread of execution or cache memory or the CPU, central processing unit. There is a I/O request and there is a data conversion and there is an interruption. But the device memory directly access without interruption of CPU using DMA concept from the main memory. It is actually called a von Neumann architecture. So we get into understand this concept technically and more deeply in the upcoming videos. Thank you, dear learners, for your passion listening about the computer system operations. Thank you so much.